Assalamualaikum and greetings everyone. We are still on partial derivative. Today I'm going to explain to you what does partial derivative means geometrically. If you recall from high school, if you're given y equals f of x, then if you take the derivative of this, then what you have is ordinary derivative. You can write it down as dy dx or df dx, or you can use the prime symbol, or you can use y. So what it means is it represents slope of a tangent line on the curve. Okay, so for example, say here you have say this is x naught, then this line here is the tangent line of the curve at that point. Okay, so that would be f prime at x naught. Now if you're here, let's say this is x1, then the slope of a tangent line on that curve at point x1 would be different from at point x naught. Okay, so dy dx or df dx represent slope of a tangent line, and it can also represent, apart from slope of a tangent line, it can also represent the rate of change, the rate of change of y with respect to x. Okay, so you want to know what happened to y if you change the value of x. Will it increase, decrease, or neither? Okay, so that is the interpretation of ordinary derivative. So it can represent slope of a tangent line or rate of change. Okay, so now we can expand that to function with two independent variables. So let's say you're given z equals f of xy. So if you plot this in xyz space, what you get is a surface. We will learn about this in chapter 1, inshallah, in week 3, where we can learn how to sketch a surface. So given z equals f of xy, if you sketch this, it's going to be a surface in xyz space. So here we have y-axis, x-axis, and z-axis. So here I have sort of sketch. Let's say this is our surface, z equals f of xy. So remember from the previous video, if you find partial f partial x, what you do is you hold y as a constant. So zx or fx, you differentiate with respect to x, but you hold y as constant. So when you hold y as constant in 3D, y constant represent a plane. Y constant is really a vertical plane. A vertical plane. Excuse me. So let's say now you have y equals y naught. So here we have y equals y naught is really a vertical plane. Okay, so it's a vertical plane because on this plane all the y coordinate will have the same value, which is y naught, but x and y varies. Sorry, x and z varies. So when you intersect the plane y equals y naught with the surface z equals f of xy, which is this surface, okay, you end up with an intersection curve. So let's say here we have the intersection curve. So the intersection curve in this case is represented by this curve. Okay, so here the intersection curve, the curve there is an intersection between the surface z equals f of xy with the plane, the vertical plane y equals y naught. So on this intersection curve, we will have different points. So partial f partial x will represent the slope of the tangent line. So on this intersection curve, we have different points. So at different point, we have different slope of a tangent line. So for example, here, this is the tangent line. But if it's here, let me change the color. If it's here, then the tangent line would be different. So partial f partial x here represent the slope of a tangent line on the intersection curve when we hold y as a constant. So it's very similar to function with one independent variable. It also represents slope of a tangent line. And here it also represents slope of a tangent line. And here for partial f partial y, you hold x as a constant. So x as a constant is a vertical plane as well. So here we have a vertical plane. X equals, let's say, x naught is a vertical plane. Because on this plane, all the values, the value of the x coordinate is the same. It's x naught. Okay. All right. So here we have a surface. Z equals fxy. So this is our surface. Z equals f of xy. So the intersection between the surface z equals f of xy with the vertical plane x equals x naught will create an intersection curve. Okay, so here we have an intersection curve. So this is an intersection curve between the two surfaces, z equals fxy and the vertical plane x equals x naught. So on the curve we have many points. So at different point we have different slope of tangent lines. For example, if you're here, then the tangent line would be like so. But excuse me, if you're here on the curve, then the tangent line would be different. So partial f partial y represents slope of a tangent line on the intersection curve, which is the intersection between the two surfaces. Okay, so it's very similar to function with one independent variable. Partial f partial y represents slope of a tangent line where you consider x as a constant. Okay, all right, so that is one interpretation. The other interpretation so now we're back to function with one independent variable. Apart from slope of a tangent line, we can also consider dy dx or df dx as rate of change of y with respect to x. So in function with two independent variables, we can also what is that 2 doing here? Here we can also consider shouldn't be a 2 there. We also consider partial derivative as rate of change. Okay, so partial derivative is the rate of change of a multivariable function. So let's say you have this. So here we have two independent variables. A partial derivative is the rate of change of multivariable function when we allow only one of the variables to change. So if it's partial z partial x, meaning that we want to know that would be rate of change of z with respect to x. So we hold y as a constant, we only vary the value of x. So we want to know what happened to z. So that is considered as rate of change. Okay, I'm gonna continue with the example in the next video. Thank you.